Assalamu alaikum, my name is Iram and I am going to present the topic inverse Laplace transform. We know that Laplace transform transforms the function from time domain to frequency domain. So inverse Laplace transform is opposite of it, and inverse Laplace transform takes a function of complex variable of a frequency and yields a function of a real variable time. Both Laplace and inverse Laplace are used to solve differential equation in simpler ways. Now come towards the elementary properties of inverse Laplace transform. So first is linearity property. If a and b are any constants and g1 and g2 are the Laplace transform of g1 and g2 respectively, then the inverse Laplace transform of a function which is ag1 plus bg2 will give me a function which is transformed into time domain ag1 of t and plus bg2 of t. So second property is first translation property, or also known as shifting property. We know that let inverse Laplace transform of a function g of s give me the function g of t, then inverse Laplace transform of a function g of s minus a, then it will give me ea of t gt. Third property of inverse Laplace transform is that of an integral. If I am given that we have to take inverse Laplace transform of a function g of s over s, so it will give me the inverse Laplace transform will give me integral having limit 0 to t g of t dt. Inverse Laplace transform of derivative will give me minus 1 power n t of n and f of t, and multiplication by s. If I am given with a function which is multiplied by s and I have to take inverse of that inverse Laplace of that function, then it will give me function in time domain. Divine by s. If a function is divisible by s and I have to take inverse Laplace of that function, then the property is that it gives me integral having limit 0 to t and f of u du. So inverse Laplace transformation of product of two functions, which is also known as convolution theorem of f and g. So if I have to take the product of that two function, it will give me integral of having limit 0 to t f u and g t minus u du. So methods of finding inverse Laplace transform. First method is using the tables. By using a linearity property, we can take inverse Laplace of given function by using tables of inverse Laplace transform. Using partial fractions, if the given function is a rational function, that is f of s is equal to p of s over q of s, where p and q are polynomials in s with no common factors, we can obtain inverse transform of individual terms by partial fractions. If denominator doesn't factor nicely, then we try completing square method. So third is using technology. Some software packages that do symbolic algebra can find partial expansions very easily, through which we can find inverse Laplace transform easily. For example, Mathematica, MATLAB, MathCAD. And the other method is using unit time function. The unit time function is defined as a function having value 0 if time is less than 0 and value 1 if time is greater than 0. So that is u is a function of time, and u has value 0 when time is negative. Before we flip the switch, the value 1 time is positive, and from which we flip the switch. So graph of f of t is equal to u of t is the following graph gives me the unit step function. This is the table which have inverse Laplace transform of some basic functions. We can easily put the values of that and can easily solve the questions easily in less time. Then the importance of inverse Laplace transform is that it is very useful to know for the purpose of designing a filter, and there are many ways in which we can calculate it drawing from many disparate areas of mathematics, and nevertheless assist the users in reaching the desired time domain signal that can be then be synthesized in hardware or software for implementation in a real world filter. So examples of numerical approximation of inverse Laplace transform are exponentially decaying sine. So exponentially decaying sine, let's plot the results along with the theoretical values for the exponentially decaying sine function. So first I have plotted the command syms, and in which I have explained and defined the variables I am going to use. I have defined the time limits a and omega. So we have put the commands and the following commands. After putting following commands and after labeling the plot and giving the titles to the plot, I will get the following plot of a sine decaying function. So examples of inverse Laplace transform by hand are, for first example is determine the inverse Laplace transform of signal x of s is equal to 2 over s plus 1 s plus 2 with simple. So for following this, we have to first solve it by taking partial fraction, and after taking partial fraction we get the answers of the variables a, b and c respectively, and after getting these answers we have put these values in the formula. So then we have to take the inverse Laplace transform because we get the function separately. So after putting the and taking the inverse Laplace and 1 over s, we have know the value from the tables. By using that values we put the value and get the answer. So we can also plot that function in MATLAB. So first we have to define the variables, which is s and t, and we define the value of f, and after taking inverse Laplace transform we get the same function as we calculated by hand. Now the next is inverse Laplace transform. We see the importance that it returns the Laplace inverse Laplace transform will returns us the function in f domain, and by default the independent variable is s and the transformation variable is t. Then if f does not contain s, inverse Laplace transform uses the function sym var. So in this example, we see this that inverse Laplace transform of symbolic expression, how we use it. We compute the inverse Laplace transform of 1 over s square. So after taking the inverse Laplace transform, we get the answer t. So default independent variables and transformation variables are plotted as, if I have a function s 1 over s minus power square, so the independent and transformation variable here are s and t. So we get the answer after taking inverse Laplace transform. So next is specification of the transformation variable as x. If we specify only one variable, that variable is the transformation variable, so independent variable is still s. So specify both the independent and transformation variables as a and x in the second and third arguments respectively. So after defining the variables and after taking inverse Laplace transform, we will get the answers. Third is inverse Laplace transform involving Dirac and Heaviside functions. So we can easily found for some functions we get, after taking inverse Laplace transform, we get the Dirac and Heaviside functions. Inverse Laplace transform of array inputs. If we are given to find inverse Laplace transform of the matrix M, we will specify the independent and transformation variable for each matrix entry by using matrices of the same size when the argument are non-scalars, and inverse Laplace acts on them element wise. For example, after defining the variables, the value of m vars and trans vars, the inverse Laplace transforms of m vars and trans vars will give me the following answer. So if the inverse Laplace transform is called with both scalar and non-scalar arguments, then it expands the scalar so to match non-scalars by using scalar expansion, and non-scalar arguments must be the same size. After defining the variables, inverse Laplace transform of that functions will give me the following answers. If inverse Laplace transform can't be found, then what we can do? If inverse Laplace transform can't compute the inverse transform, then it results in unevaluated call to I Laplace. So return the original expression by using Laplace. That is, if I have a function which is exponential s and I Laplace after taking that f of s and t with respect to t, so I Laplace will give me that function. So I have to return to first Laplace and it will give me exponential of s. Inverse Laplace transform of symbolic function. When the first argument contains symbolic function, the second argument must be a scalar. So in this command we see that after performing in Laplace transform, I have defined f1 which is exponential of x and f2 which is x. So I Laplace command will give me f1 f2 x comma a and b in brackets. So I Laplace its answer would give me the function in Dirac notation. 3D inverse Laplace transform curve. So we can also get the 3D picture of a function inverse Laplace curve. So if I have a function, we have to solve it by using the command mesh grid and limits from minus 10 and 0.1 and minus 10 to 10 having parts of 0.1, or I am given with the function t equals to x plus j multiplied by y, and z is defined as, so after giving the command mesh x y z, I will get the 3D plot which is as given in the picture. So next is role of inverse Laplace transform in solving ODEs. We can easily solve the ODEs by using Laplace and inverse Laplace transform. So we can solve it by using the problem of RLC circuit. I want to mention here that every circuit is first solved by Laplace transform, and then inverse Laplace transform would take its part further before plotting. So it can use the Laplace transform to solve differential equations with initial conditions. For example, we can solve resistance, inductor, capacitor circuits such as the circuit given. So I have to solve this by using by hand as well as by MATLAB. So here one is a capacitor R1 R2 is given, then currents in are represented by I1 I2 and I3, inductance is in L, and 4 is capacitance, that is C farad, and electromotive force is in volt, E of t charge in coulomb. So after applying Kirchhoff's voltage rule and current laws to get the differential equation to the for the RLC circuit, so we get the following equations. So first and second step is that we have to first declare the variables, because the physical quantities have positive values, and set the corresponding assumptions of the variables. Let E of t be an alternating voltage of 1 volt and declare the differential equations. So these are the commands. In the third step, we first we have explained that what is E of t, what is we have defined all the variables defined here, which is voltage. I have given that it is 1 volt, and we have also defined the di of 1 and dq, and equation is also written which is previously explained. So in the third step, we assume the initial current and charge value here, which is as I0 and Q0, which are both initially 0. So declare these initial conditions in these steps. So after defining these conditions, In the step 4, we solve the equation and compute the Laplace transform of equation 1 and equation 2. After defining in step 5, the function solves only for symbolic variables, and therefore to use solve first substitute Laplace of I1 of t and t of s, and Laplace q of t and t of s with the variables I1, L1 and ql of t. So in step 6, we solve the equations for I1 LT and QL of t. After solving them, in step 7, here we use inverse Laplace transform and calculate I1 and Q by computing the inverse Laplace transform of I1 LT and QT, which we have solved in the step 6. Simplify the results, and after simplification command, we suppress the output because it is very long. So in step 8, substitute the values, and we have taken, and these values, after putting these values, plot need numerical values to plot, because we can't plot if we have some variables in it. So after putting the values, we can easily get the plot of the example. So here we put the values as variables, var, vars, these variables, and after putting their values in the solution, the step 9 is plotting. So we get plot here. Plot the current and charge, show both the transient and steady state behavior by using two different time intervals, that is from time 0 to 10 and 5 to 25. So I plot all the plots in one frame by using command subplot. So we get the first plot by using subplot 2 to 1, and I get the following plot. So you see it is the current plot. And in the second plot, I have plotted the current and charge as well. We see the variation of current and charge with respect to time. We see then in the second diagram is for charge, and then we have given the transient state, which is transient state. For transient state, we get the following, and the steady state is the following. So you say in one graph we have discussed both the state, which is the transient state and the steady state of current. So the next is for charge, transient and steady state, and they are easily determined in these by plotting these values. We get the following graphs and plots. So step 9 is analyze the results we have got. Initially, the current and charge decrease exponentially. However, over the long time term, they are oscillatory, and these behaviors are called transient and steady states respectively. With a symbolic result, you can analyze the results property, which is not possible with numerical result. So visually inspect I1 solution and Q solution. There are sum of terms. Find the terms by using, and then find the contribution of the terms by terms. Our 0 to 15, and the plot show the transient and steady terms. So here are further I1 terms, and I have used that by myself. I have used children. We can use any of the term. So subplot, after subplotting, we again get all the plots in one frame. So we get after plotting these commands, I get the plot for charge and for the charge and current terms, and their steady and transient states as well. So we see that current terms and charge terms, their graphs, and we use the following commands, which is fplot q term 0 to 15. So we get the graph like that from 0 limit to 15 limit, and in y limit we put -2 to 2, and we got the following results. And the fourth here command is title. We give that title as charge terms, and for current terms we give the title current terms. So inverse Laplace transform on Mathematica is that using Post formula, Emil Post 1930 derived a formula for inverting Laplace transform that relies on computing derivatives of symbolic order and sequence limits. Here post invention formula is implemented using the new capabilities of D and discrete limit. Post invention formula may be stated as follows, which is L inverse of f of st, limit goes from k goes to infinity, and minus of k of k over t and power k plus 1, and partial k over partial s of k having function f k over t over k factorial. So we can plot this function in Mathematica. So in Mathematica we get after plotting these commands, we get the following plot having this plot is for n equals to 40, we get the red curve. For n equals to 16, we get the green curve, and for orange line we get n equals to 12, we get the orange curve, and for blue we get for n equals to 6. So we use here which commands I have used here. This formula is plotted here in Mathematica, and we give approximation for n values. We get as 6, 12, 16, 40, and we give by using this commands we get the 5 plots in one frame, and after evaluating and giving the value of t, which is from 0 to 4, we get in ABC in x-axis the time is from 0 to 4. So plot legends command give us plots in one frame. All the plots and image size is 300. So these for the simple commands in Mathematica, we can also go for it. which is inverse Laplace transform in Mathematica. These are the commands we used and we get the answer as well. The previous commands are in MATLAB, while these commands are Mathematica. So inverse Laplace transform of log s plus a or log over s plus b will give me the following answer. So the above results having parameter a and b, we can also solve these commands in Mathematica. The other commands are for inverse Laplace transform of a bivariate function. So for bivariate function, we get the following commands, which is inverse Laplace transform 1 over under root 1 plus pq, where p of q and x of x comma y will give me the following answer. So logarithm of a rational function can also be found by using inverse Laplace transform. By plotting the function, we have to use the command inverse Laplace transform and placing the function, and we will get the answer. We can also plot that function by putting the limits, and t goes from 0 to 15, and we get the following plot. So these are the plotting in Mathematica. So other function is that I have taken a function, and by using inverse Laplace transform form, and we can also plot this function obtained by just putting the answer we got, and we after placing the limit in plot range, which is from -30 to 30, we get the following results. This is from my side. Thank you.